Modern data centers are rapidly scaling up to the 1 or 2 gigawatt scale. At this capacity, they operate less like traditional IT facilities and more like high-density AI factories. This concentration of GPU processing power creates extreme localized thermal densities that challenge conventional cooling systems. Facilities manage this heat using liquid cooling infrastructure, monitored by static point-in-time sensors. But relying on fixed sensors to protect high-density computing is a systemic vulnerability. A fixed sensor array cannot capture fluid environmental changes. It will miss highly localized thermal drafts, and it cannot detect microscopic misalignments in the liquid cooling manifolds until the ambient temperature of the entire aisle has already shifted. We can see this exact infrastructural complexity at the Stargate facility in Abilene, Texas. It is a multi-million-dollar environment characterized by extreme power density and aggressive HVAC airflow. Because the GPUs in these racks are packed so densely, a single undetected hotspot does not stay isolated. It cascades, radiating heat to neighboring hardware and triggering localized thermal runaway. Legacy building management systems pull data in intervals of minutes. Protecting modern AI hardware requires a system that detects anomalies and triggers responses in milliseconds. This environment dictates that thermal monitoring cannot be solved by installing more static sensors. It requires mobile spatial intelligence. The theoretical solution is to deploy autonomous multi-rotor drones to physically patrol the server aisles, actively scanning for localized heat signatures. Translating that theory to the physical world introduces a massive roadblock. Navigating a lightweight drone inside a server aisle means flying directly into intense, unpredictable exhaust airflow generated by the HVAC systems. You cannot simply place an experimental drone into a live GPU cluster to test its flight controller. The physical and financial risks of a collision are unacceptable. To safely design and validate an autonomous physical intervention system, we must first build a predictive digital twin. This is Project ThermalSight. It is a zero-risk, high-fidelity 6-stove simulation environment built in NVIDIA Omniverse. 6-stove stands for 6 degrees of freedom, meaning the simulation accounts for the drone's ability to move and rotate freely across all 3 spatial axes. The physical twin, an Iris quadcopter, and its complex multi-rotor aerodynamics are simulated entirely using Sim 4.5 and the Pegasus simulator extension. This architecture provides a mathematically accurate sandbox. It allows us to train, tune, and validate both the computer vision models and the navigation logic on synthetic data long before physical hardware ever leaves the ground. The digital twin operates on a continuous OODA loop. The system must constantly observe, orient, decide, and act. This loop dictates the chronological flow of data. It bridges the physical physics simulation over to a custom Python decision node, which acts as the brains of the drone. The loop begins with the observe phase. The simulated Iris quadcopter generates synthetic point cloud and RGB thermal data from inside Sim. A point cloud is a dense set of data points in 3-dimensional space, typically used by LiDAR sensors to map physical surfaces. This raw telemetry is published continuously at a frequency of 50 Hz. The transport mechanism handling this is a set of ROS2 OmniGraphs acting as the middleware. The system then moves to the orient phase. Raw sensor data contains mechanical noise and is entirely useless to a control system without context. To build that context, the system fuses the 6DOF pose data and applies YOLO computer vision algorithms to the synthetic thermal arrays. YOLO stands for You Only Look Once, a high-speed object detection algorithm that processes entire images in a single evaluation. By filtering out mechanical uncertainty, the orient phase generates a high-confidence state estimate. The system now has the exact coordinates of the drone and a verified map of the surrounding temperatures. With a clear state estimate, the Python node enters the decide phase. It has to compute real-time motor adjustments to counteract the simulated HVAC turbulence pushing against the drone. Spatial intelligence across 6 degrees of freedom appears mathematically intimidating, but the underlying logic is rooted in foundational control theory. The perfect analogy for multi-rotor flight is the classic 1D inverted pendulum problem. To keep the pendulum balanced upright, the cart at the base must constantly make micro-adjustments along a track. A drone and a pendulum share the exact same pattern. They both have unstable dynamics, they both rely on noisy measurements, and their decision policies are both governed by a PID controller. A PID controller is a mathematical feedback loop that constantly calculates the error between a desired set point and a measured process variable, applying a correction based on proportional, integral, and derivative terms. Drone multi-rotor control is simply the 1D pendulum problem scaled geometrically to 3-dimensional space. Instead of a cart moving on a flat track, you have 4 rotors adjusting thrust in the air. You can see exactly how the theoretical math translates to the Python code. The core error calculation, the integral accumulation, and the derivative correction mirror each other entirely. This custom spatial PID controller calculates the precise 3D trajectory correction required to stay on course. It then strictly clips that output to ensure the requested velocity never exceeds the physical limits of the drone's actuators. Without this strict mathematical decision policy, the intense environmental perturbations in a data center would immediately destabilize the physical drone. The internal flight loop concludes with the act phase. The Python node has calculated the required correction. Now that mathematical decision must be translated into physical movement within the Sim environment. Looking at the architectural map, we can trace this return path directly from the Python node back to the physical twin. The Python node publishes specific twist commands back through the ROS2 middleware. In robotics, a twist command is a message that expresses velocity and RPM targets for linear and angular motion. The Pegasus simulator receives those twist commands and actuates the digital drone's multirotors. It physically adjusts the pitch and thrust, stabilizing the vehicle against the wind. Closing this physical loop proves the aerodynamics are viable. The drone can fly. And because it can fly, the system can now execute higher-level enterprise responses. With the low-level aerodynamic control established, the narrative focus shifts entirely to high-level operational strategy. We test the system's utility with a specific scenario. The drone is executing a routine patrol down an aisle when the computer vision model detects an unexpected spike in heat radiating from a server rack. This chart shows the live thermal telemetry. The Orient module evaluates this data and statistically classifies a thermal anomaly exceeding the critical safety threshold of 85 degrees Celsius. This classification acts as a hard trigger. The decide module receives the alert and immediately executes an operational phase transition. The drone drops its original flight plan. It automatically transitions from routine patrol into a targeted investigation phase, maneuvering closer to the affected server rack to capture high-resolution localized data. The OODA loop allows the system to scale its intelligence. It seamlessly transitions from managing reactive flight stability to executing proactive infrastructure inspection. A drone holding position and gathering data is a localized action. To prevent a facility-wide cascade, the system must communicate the threat to the enterprise layer. If we look at the bottom half of the architecture diagram, we see the enterprise intervention layer. The Python ACT module bypasses the drone entirely and executes a direct REST API post call, sending data out of the simulation. This API call pushes structured telemetry, including the specific rack ID and the exact temperature, directly into the Palantir AIP ontology. An ontology is a structured data model that maps the relationships and states of every physical asset inside the data center. Palantir AIP digests that telemetry and instantly updates the live facility knowledge graph, flagging that specific server node as degraded. This state change triggers the final autonomous response. An MQTT message is published directly to the facility's IoT infrastructure. MQTT is a lightweight messaging protocol designed specifically for machine-to-machine communication. The message instructs the facility to automatically increase the liquid cooling flow rate exclusively to that degrading rack. The digital twin identifies the threat, alters the flight path, maps the exact location, and physically intervenes at the facility level. It prevents catastrophic hardware failure before it can ever truly occur.